Okay, hi everyone. We're back to finish chapter 3. The final thing that we need to do is to do an example problem from the book related to um, section 3.7 on predicting stability of immersed and floating bodies. Now remember, this is important for determining the stability of ships and buoys and other floating objects. And if you remember from the notes, we had talked about immersed bodies, but also floating bodies. And what we had determined is that if the metacentric height, the metacentric height was positive, then the object that's in the water, that's floating in the water, will be stable. However, if the metacentric height, GM, this is GM, if it is negative, then the ship is, or the object is unstable. And so what we'd like to do, and we had a method here for basically going about determining the stability. But what we'd like to do today is do example 313, 3.13, and determine whether this situation is stable. At first glance, you would think that it would be. It looks like a stable situation. We have a block of wood that's 30 centimeters square in cross section, as you can see from this diagram here, and it's 60 centimeters long. It weighs 318 newtons, and the question is, will the block float with its sides vertical as shown? And so the way that we are going to go about this is kind of a two-pronged basically two steps. We need to apply force equilibrium, basically the buoyant force, to determine the depth of submersion of the object. We're going to use this in both cases to find out kind of the volume. This is really going to give us volume of the displaced fluid, which is very important for us. And then the second thing we're going to do is we're going to determine stability, and we do that obviously by determining the metacentric height, GM. And if we remember, GM is equal to the area moment of inertia at the water line of the basically the shape at the water line. We'll talk about that more in a minute, minus the distance between the center of gravity and the center of buoyancy. So let's go ahead and do this for this condition right here. And so our force equilibrium is going to be, if we draw a diagram here of the block sitting in the water, it's supposed to be a square block, and we define y to be vertically upward, we know that we're going to have the weight of the object down in the minus y direction, and it'll be balanced and equal and opposite force by the buoyancy force. And this will allow us to find out the depth of submersion since we know the cross section. So if we write this out as a force diagram, the buoyant force in the positive y direction minus the weight in the minus y direction, these forces have to be zero because the object is static. And so we can solve for the buoyant force. We know that the buoyant force is equal to the gamma of water times the volume. And we don't know the volume of the displaced fluid, but we do know it's that one side is 30 centimeters and the length of it, the length of it is 0.6 meters. And we don't know the depth of the submerged fluid. So that's what we're going to be looking at. And we know that that has to equal the weight. This must equal to weight. of the block, which we know is 318 newtons. So we can rewrite this equation now. It's going to be 318 newtons. It's going to be divided by gamma, and in this case we're just going to use 9810 newtons per meter cubed, and the cross-sectional area, which is 0.3 meters times 0.6 meters, and that will give us the D. And in this case, D turns out to be 0.18 meters, or 18 centimeters. So we know D is 18 centimeters, that it's riding that 18 centimeters are submerged and 12 centimeters are above the water line. So that is going to be important, because when we do the second part of our problem, which is to find the metacentric height to determine stability, we need to know the volume of the submerged fluid, V. That is, and so we're going to use that 18 to calculate that. And we also need to know the distance between the center of gravity and the center of buoyancy, which I'll show you in a minute. So let's piece these things apart. So we know these things are where I00, this is, and this is a key point about doing these problems, this is basically the cross-sectional area. Try to draw a little volume here. It is the cross-sectional area about the water line here. So this, the water line is kind of along this line and along here. So in this case, this is a rectangle, basically of a cross-sectional area of 30 centimeters by 60 centimeters. And we need to determine, sorry, that's a centimeter. We need to determine the moment of inertia about that plane, if you will, the water line. And so for this rectangle, that becomes, if we look that up, that is 1/12. In the book, I think it's given by B times H3, but basically this is 1/12 60 centimeters times 30 centimeters cubed is our moment of inertia. And in this case, V is going to be 18 centimeters. This is the volume of the displaced fluid now. Let's do it this way. 60 centimeters and times 30 centimeters. That is the volume of basically of the displaced fluid, or the submerged part of the block when it's in this orientation here, right here. So let's, and then also another interesting thing is that we have to know the distance between the center of gravity and the center of buoyancy. And the easiest way to do this now that we've got this picture of this submerged object, it's a square, and we know that the center of gravity is right in the middle of that. And we also know that the center of buoyancy is halfway down, halfway through here. So the center of buoyancy is here. It's not a great picture, but the easiest way to determine this is to note that is to do things relative to the base. This is 15 centimeters, and from the base of the thing up to here is 9 centimeters. That's a centimeter. So the distance CG between these two, between the center of gravity and the center of buoyancy, between the center of gravity, the center of gravity and the center of buoyancy, is simply 15 centimeters minus 9 centimeters equals 6 centimeters. Okay, So let's pull all this together in the next slide then. So GM is going to be equal to this over the volume minus CG. And I'm going to start over here a little bit further over on the side here now to give myself a little bit more room. This is going to be basically 1 over 12 times 60 centimeters times 30 centimeters cubed divided by the volume, which is 18 centimeters, 60 centimeters times 30 centimeters. And this is all going to be subtracted. We're going to subtract off of this 6 centimeters, which is the distance between our center of gravity and our center of buoyancy. And we can see that we get some cancellations here. And what we're left with here is basically 30 centimeters squared divided by 12. This factor here from the numerator goes into the denominator, and all that we're left with in the denominator is an 18 centimeters, and we're going to subtract off 6 centimeters. And what we get is 900 centimeters squared divided by 12 times 18 centimeters minus 6 centimeters. And this whole, this quantity here is in centimeters, and it turns out that that equals 4.167 centimeters minus 6 centimeters. So in answer to our question, this is GM. GM obviously turns out to be a negative number, minus 1.833 centimeters. So in answer to our question, is this stable? The answer is no, it is unstable, which was not my intuition the first time I saw this problem. So it's unstable because of the minus sign here. So the book then goes on to show that maybe we should calculate this situation and determine whether or not the block is stable under these conditions. And so let's go about doing this. Again, we need to do the force equilibrium again. You'll see why in a minute. It may not be intuitively obvious why we need to do this. But when we do this again, this time we're not interested in determining that we're trying to find how much of the volume is submerged in this situation. You can see the geometry is a bit more complicated now. I'm just going to draw a line here for a second, but you can see that this is basically the submerged volume. That's going to equal the submerged the weight of, that's going to be the volume of the fluid displaced as well. And I'll go ahead and delete those lines. I don't want to. Oh, it's not going to let me. Oh, there it goes. So so we have to determine that volume. It would be good for us to know that. So let's just do the force equilibrium again. It's the same equation, and we know the weight again is 318 newtons, but in this case we're interested in the submerged volume. So we're going to just leave this as V and just calculate that entire volume. And for this situation, and so what we have is V is just equal to 318 newtons divided by 9810 newtons meter cubed, and the volume in this case turns out to be 324 meters cubed. So that's our volume, and we're going to need that later on. Now, what about if we wanted, now the next thing that we need to do is determine this width. We need this width because we need to know basically the dimensions of the area of this object at the water line. This is what we're going to use to calculate the moment of inertia. Again, that's very important. So we need to know this W, because if I draw a cross section of the area that's at the water line, if we're looking at the top of this, we would see W and then the length. We would also see kind of the center line of the crest of the triangle, but this would be W, and this would basically be our length of 60 centimeters. And this is going to be what we're going to use to determine the area moment of inertia. We need that area. It's going to be about the moment of inertia about that area. So let's go ahead and do some geometry to determine that. The book shows, the book just kind of throws this out, that the volume of the displaced fluid, which we just calculated to be 0.324 meter cubed, they calculate that to be the original volume of 0.3 meters squared minus times 0, boy, this writing too fast today. Something's going on with my pen, just a second. 0.6 meters. And that's the original volume, the total volume of the block. But the book throws this out, this value out, and then also times the length, which is 0.6 meters. Now, where did that come from? So we're going to basically use this formula to find W. We can, this is equal to 0.0324 meters cubed. So we just need to solve this simple equation for W. And but where does that come from? So if we draw a picture of the block here, kind of draw a large version of it, and the water line is here. Basically, we need to concentrate on this triangle right here. And if we blow that out and blow it up to look at it, basically this triangle ends up being, this is not going to be very well to scale, but basically this ends up being, obviously this is the dimension we want. Let me draw that long. This is W, but half of that is obviously W over 2. That's the base of our triangle is W. 1/2 the base is W over 2. But this, it turns out that this turns out to be, because it's floating like this triangle here, it's not drawn very well, but that's actually an equilateral triangle where this is also W over 2, and this is actually also W over 2. So the basically the area of this portion of the triangle then becomes 1/2 the base times the height times L, and 1/2 the base is W over 2, and the height is also W over 2, and the length is just the 60 centimeters. So that's where we get this equation of W squared over 4 times the length. And if we in fact calculate W, we get 0.18. I take that back. We get 379 meters, or 37.9 centimeters. Okay, so now we have what we need in order to find GM, the metacentric height. This again is going to be the moment of inertia, the area moment of inertia at the water line, using basically the area at the water line and minus CG. CG were given from the problem, luckily, we can see that right here. So that's going to be 5.73 centimeters, which I'll throw in here in a minute. But first of all, let's go ahead and we're going to do this very similar calculation here. The length again is just, let's do this in meters. Is that what I want to do? Yes. Let's do that in meters. 0.6 meters. And at this point, our W is going to be 0.379 meters cubed. The total volume is just what we calculated before, which was 0.0324, 24 meters cubed, and we have to subtract from that 0.0573 meters, which is CG. So when we do this, basically the moment of inertia ends up being 0.00273 meters to the fourth. The area, again, did I get that right? Yeah. 0.0324 meters cubed, and then we're going to subtract off 0.0573 meters. And what we get for this value of GM in this case, when all is said and done, we get 0.027 meters plus, which is equal to plus 2.7 centimeters. And we can see then that GM is positive, which implies that the object is stable now. So that's it. That's how we do that problem. Again, just to recap, that the key to these problems is finding the area moment of inertia of these objects. And so I'm just going to try again to draw this rectangle for this case in red. For this case, remember that this object has a length to it, and it's this basically. Whoops, do that again. That basically it's this area, or this particular rectangle that's at the water line that you calculate the moment of inertia of. And so this becomes W times this L, and since it's a rectangle, we use the familiar equation for the moment of inertia, which in this case would be 1 over 12 L with these dimensions. It would be this. So that's going to equal this. And that's true for this case, and it's true for the original case where we had basically a rectangular surface as well, but it was had a W basically, or a width of 30 centimeters in this case here, and a length of 60 centimeters. So that's it. That's it's unstable in this case when it's sitting on kind of flat, if you will, and then when it rotates into this orientation, it actually is a stable object. Okay, that's it. Thanks.